Welcome to Spring LIB.
So here's an interesting problem. Let's say we have a bullet that's been shot into a block, and the block is sitting on a frictionless track. Once the bullet and the block collide, the block is going to travel along the track and up around this curved part and eventually fly back out and land somewhere. And I'll call that somewhere that lands, we'll call that delta x. Question is, what is delta x? All right, we're given a couple bits of information. We're told that the mass of the block, that's going to end up being 490 grams. The mass of the bullet is going to be 10 grams, and it's going to be moving at an initial velocity of 50 times the square root of 7 meters per second. All right, this problem is going to have 3 different parts to it. We'll have to put those all together in order to get our answer. All right, so part number 1, conservation of momentum. What we're looking at is an inelastic collision. In conservation of momentum, we have the total momentum in a closed system is equal to 0. That means P initial equals P final. My sum of my initial momentum can be equal to the sum of my final momentums. Initially, we just have that bullet, which we called mass 2, moving. So that'll be P2 initial. And then we're going to have finally are both the bullet and the mass traveling. So I'm going to call that P final 1, 2. Or written a different way, that's going to be M2 V initial 2 equals M1 plus M2 times V final. All right, and what we're really interested here is this final velocity. So that's M2 V I2 divided by M1 plus M2. This will be a key equation because this final velocity tells us the speed at which the block and the bullet are going to travel at and arrive here at this x. All right, once it arrives here at x, that final velocity is going to be the initial velocity for part 2 of our equation. Part 2 of our equation involves conservation of energy. All right, the total energy inside a system is going, the total change in energy inside a system is going to be equal to 0. E initial equals E final. What's going to happen is initially we'll have our block that's moving. It's going to have a kinetic energy initial. And eventually, as the block moves, it's going to end up at the very, very tip top. So it's going to have both gravitational potential energy, I put final right there, gravitation, plus whatever kinetic energy was left. And that kinetic energy that we have left, that's going to be the energy that this block now travels at for part 2 of our question, another V final. All right, let's go on and expand what this is. So this is 1/2 mass 1 plus mass 2 times V initial. And I'm just going to make a little note here. We're going to call this V final. We're going to call this V final 1 for the first part of our problem. I'm just going to make a note that down here, V initial equals V final 1 from the first part. All right, so that's kinetic energy up and squared. Gravitational potential energy, that's going to be the mass of the bullet in the block times its change in height. The block is going to go down all the way up. That change in height starts from a height of nothing, up 1 r, up another r. So its change in height is going to be 2 times the radius. 2 times the radius, or the diameter. I ran out of room, plus its final kinetic energy. And that'll be 1/2 mass 1 plus mass 2 times V final squared. And again, we're going to solve for V final here as well. And this one I'm going to call V final 2 squared for part 2 of our problem. Let's solve for V final 2. And we end up with 1/2 times mass 1 plus mass 2 times V final 1. Oh, let's actually, that way you can see this pretty easily. I'm going to replace this initial velocity with this guy here from part 1. V final 1 squared minus mass 1 plus mass 2 times 2r. All right. All that is going to be times 2 and divided by mass 1 plus mass 2. And we're going to take the square root of all that to get V final 2. All right. Let me write that a little bit more clearly for you too while I'm at it. Here, we'll put times 2 over here. That way I can put my little radical sign that encompasses all of this. Everything goes under the radical. Ding. All right, and now on to part 3 of our problem. So we end up here where now this V final, I'll call that V final 2. It's going to start our kinematic part. The mass is going to travel a parabolic path. All right. So this is a kinematic problem now. Part 3. Kinematics, we do displacement, and it'll be 2-dimensional. And so this is in the x direction. We write, displacement in x times v initial x, v final x, ax, t equal. And then in the y direction, you write displacement in the y direction, v initial y, v final y, acceleration y, and time. Okay. If you look at our problem, we can tell that the displacement in the y direction is going to be negative 2 times that radius. The initial velocity in the y direction is 0. Final velocity, don't know. This one, I'm going to use a trick and say negative 10 meters per second. By the way, I'm putting negative to emphasize that we're going down. And the time, we don't know. As far as the x direction goes, well, we don't know what the displacement is going to be. But we do know that its initial velocity is going to be the velocity we found in part 2. And that's the same thing for the final velocity. That's always true for the x direction. Well, as long as there's no acceleration, which there is none. And then t is a question. All right. That said, let's see what we can do. So we need to be able to solve for delta x, but to solve for delta x, we need t. So let's get t from the y direction first. Get t, time. All right, and the equation I'm going to use to figure that out is going to be delta y equals 1/2 ay t squared plus v initial y t. Thankfully, v initial is 0. So this becomes pretty easy. If we solve for t, we end up with 2 delta y over ay square root equals time. Now we have an expression for time. Let's now get delta x. Use a similar equation, delta x. Oops. There we go. Delta x what we're actually looking for, equals 1/2 ax t squared plus v initial xt. Acceleration is 0, so we're left with delta x equals v initial x times t. V initial x, we know, is v final 2 from part 2. And then t, we'll replace that with what we got for delta y. And that's the square root of 2 times delta y. Delta y, we know, is 2r. So altogether, that becomes 4 times the radius divided by acceleration, which is -10 meters per second squared. Okay. Oh, and negative. Good. That's time. And we're almost done. All we need to do is plug in whatever the value is we get for v final 2. V final 2 we'll get from this big old expression. What a nice guy to look at. All right. And then we need v final 1 from the first part. And that'll be coming from this guy. But I'll leave you to plug in all those numbers and you would be done.